I don't know if you got to meet my student Jen. So.
Hi, nice to meet you. So you're talking today. For your work. Yeah, so I'm actually having that.
Oh, really? Oh, okay. What kind of bro? Oh, you're really? Yes.
Okay, let's start today's first session about Bayesian modeling of EEG and fMRI data. We have three awesome speakers about talking about how to use Bayesian modelings for brain imaging data. So our first speaker is Fiecas from University of Minnesota.
So first of all, thanks to Meja and the organizing committee for the invitation. And I also want to thank you all for coming up here at 8:30. I've given Meja a lot of flack for making me talk at 8:30. Even though it's central time for me, 8:30 is still 8:30. I do apologize to Martin that I don't have my Latin shirt. I know you wanted to see my deep V. I didn't bring it with me. I did not plan it in advance. So this is work by my PhD student, Brian Hart. For those who have known the things that I do, you might be surprised that Mark is doing Bayesian nonparametrics. The answer is no. Brian Hart does Bayesian nonparametrics, not me. So I will defer all questions about Bayesian nonparametrics to Michele and Marina. Those are the two experts of that here. So I will answer the time series part. And I'm also keeping this relatively light on the technical side. I'm going more big picture. I believe I only have one equation, for instance. Let's get straight into context to kind of give you an idea of what I'm going to be, or what I'll try to accomplish in the next 21 minutes or so. There are 4 questions here. I had in my title microstate analysis, but given how the field has been moving, specifically in fMRI, it's been using the term dynamic connectivity. It's very similar in spirit, and then we'll talk a little bit about this. The EEG literature has been more on using that word microstate analysis instead. The context here is on, I'll be using the data, EEG data from the Minnesota twin study, which has been going on since however many decades now. And one of the big motivations for the Minnesota twin study has always been, what are the contributions of genetics to whatever phenotype that we see. And so in this case, it's going to be on EEG features, namely on dynamic connectivity or the microstates themselves. There's probably a good chance that you may not have seen imaging genetics before. I believe Wes Thompson will be talking a little bit about that later today with respect to ABCD, the ABCD study. So I'll give you just a very big overview of that. The bulk of this talk is going to be on the third question here. Like, okay, now that we have the fundamentals, then how do we do this? Given that the Minnesota twin study has a twin design, how do we take advantage of that? And just a little bit of my thoughts on what I think that we can do to improve upon this work, and also just the broader microstate analysis literature, where I think that we could go. So that's kind of the big overview. So let's start with the first one. What is this dynamic connectivity microstate analysis? As I said, I'm going to use them interchangeably here. So if you've been doing a little bit of this work on dynamic connectivity in recent years, you may have seen that it's kind of exploded, especially in the fMRI literature. I would say that, at least for me, I feel like a lot of it is really driven by Vince Calhoun's work on using GIFT in MATLAB for doing those ICA time courses, and then getting the dynamic connectivity in resting state fMRI. So the stats folks have been going along with this as well. So just showing you 2 papers here that does it. So we've got this amazing JASA paper that came out not too long ago. Look at this all-star lineup there. Lynn Allen, Vince Calhoun, Marina Benucci. I don't know who this guy is. I think they felt bad, so they wanted him to get a little bit of playtime too. Then there's this Bayo, I don't know who he is. Doing things on more in the EEG world. This was on dynamic connectivity and fMRI. Using these 2 papers in particular, there is a whole lot, but these 2 have some similar context and framework to what I'll be doing. namely if you know about the Markov switching vector autoregressive model, because that's going to come into play in this talk. And just a little bit of shameless advertisement that so my student Jun Young Park has also been, that was his talk yesterday. So now for task-based fMRI. If you want a very nice overview of what is this idea of dynamic connectivity, a very readable paper is this one in Neuron by Vince Galvin. So he just goes all out on it. Like, these are the many ways we can talk about it. I know that in recent years, Martin and his groupies over there have been pumping out some works on big overviews as well. So I believe it came out in Neuroimage a year or two ago. This is a little bit older, but it's fairly readable, so it's something I would suggest. Now, these are recent works, and as I was saying, that is kind of driven by this idea of, dynamic connectivity analysis in resting state fMRI. But this idea of things are changing over time in neuroimaging has been around for many decades. And so to just kind of give you two papers, I don't remember his first name, but Lemon here. I mean, if you can see this first paper, 1987, and this one in the late 90s. So microstate analysis, what it posits is that if you imagine that you have brain activity in the broadest sense, interpret it however way you will, that there are states that give rise to the activity that you observe, which sounds like a hidden Markov model, and that's pretty much what it is that they're doing, and which sounds like exactly what Vince Galvin and all that GIF stuff does. And but they've been doing this for at least in the EEG world for decades now. And they've done it in the sense of in the spatial sense, that as we go over time, then different electrical activity that you see in the EEG scalp electrodes will be quote unquote active at certain times, and will switch between different states. I mean, that's microstate analysis. But one of the big differences between EEG and fMRI is the time and spatial scale. In the EEG world, we're talking about many samples per second. Often, they're sampled at 32,000 kilohertz, 32,000 hertz, 32K, and then down sampled to 128 hertz. fMRI is on a much smaller scale, right? We're talking usually, one sample every 2 seconds. So if you think about then, why they call it microstate. Because even in a single second, you already have a lot of data there. And so in the EEG world, things are switching fast. Now, one of the things that's been really fascinating about this idea of dynamic connectivity and in fMRI and microstate analysis is that people have been doing this joint modeling of the two. And they've shown that there is some correspondence between the microstates themselves and dynamic connectivity. So I'm not going to show any of those papers here, but but there's definitely some work on that. So that's kind of just the context that I'm working in. So let's go into imaging genetics. So this is just going to be a very brief overview. So one of the well, let's just get straight to the figure here. So consider the following figure. You have on the left genes, on the right brain, and sorry, in the middle is the brain, and on the right is the phenotype of interest. What we've seen a lot in this, yesterday, and also in the posters on 2 days ago, it's primarily been the middle to the right. Namely, you have whatever phenotype of interest, let's say brain activity that's attributed to motor function, and then you can then ask the question, which regions of the brain are engaged in this activity, or which regions of the brain are quote unquote functionally connected because of this activity. So that's phenotype. So you could have, say, a working memory task, for instance, and how does the brain what is the brain like whenever it's engaged in something, whatever that may be. So you could also, so we heard a whole lot of talks about Alzheimer's disease yesterday. So you could also ask a question, any differential activity patterns or connectivity patterns as a result of Alzheimer's relative to, say, mild cognitive impairment. That's still, middle to the right. Now, in the completely different community, right, is if we start looking at our colleagues who work in statistical genetics, they ask the left to the right, which is like a GWAS, for instance, which SNPs are associated with, say, Alzheimer's disease, or which SNPs are associated in whatever it may be. So imaging genetics combines these two worlds together, namely that if we have, say, APOE is associated with Alzheimer's, but we also know that Alzheimer's is associated with with memory and other types of cognitive function, then perhaps it is the gene that affects the brain, which then leads to the changes that we see as a result of Alzheimer's disease. So it's this combination of the two worlds, and that is imaging genetics. We heard some bashing about ADNI, and I do agree with some of it. It's an extremely noisy data, but one of the things that's really nice about it is it does have SNPs and imaging. So if you're interested in publicly available data to do imaging genetics analysis, ADNI is one of them, and one of the recent studies Wes Thompson will be talking about is ABCD. So baseline imaging data they just released, and I believe they also just released the SNPs, and it's going to be a longitudinal study as well. So this is a very, very difficult problem just generally. And for those who are in Southern California, just a little advertisement for Irvine here, the Imaging Genetics Conference is held here every year. I think it's still going, Kelly, can you confirm? Every January, February, roughly? So, yeah. Okay. And I've gone to that a couple of times, and there's less than 5 statisticians. So there's really not a whole lot of people involved in it. And it's something that, if it's something that you're interested in, that conference to me is, gets me exposed to, say, what the problems are if you want to think about this. To kind of tie this now, so that's, this is what we're going to do. Now, when it comes to, say, dynamic connectivity, that can be, say, on the right side. Whatever feature they extract from dynamic connectivity, for instance, the number of states in a dynamic connectivity analysis, if you were to do, say, hidden Markov model, or how long those states are. That could be the quote-unquote phenotype of interest. Then you can start asking a question, well, do genetics play a role in the variation in that phenotype? So there's this paper released in PNAS very recently. So I'm also copying and pasting just a snippet of the abstract here. And I'm highlighting the word, the phrase here, is heritable. In the very bottom. The abstract's fairly rich, and if you want some quick takeaways, there's actually just reading the abstract of this paper is fairly. I learned a lot just from that. But the point of what I'm trying to point out here is that so they were essentially showing that the dynamic connectivity has some heritable properties, and so that's what we're gonna. So they did this in. I believe it was FMRI, and then so we're going to do this in EEG. Just a little quick overview of the data that I'll be looking at. So this is from the Minnesota Twin Study, actually just a subset of it. I'm looking at just a large number, relatively large number of female twin pairs. There's actually way more than this, but Brian was having problems just getting it memory-wise to fit, so we were doing some subsampling, so namely we restricted to females. Roughly 250 female twin pairs, 160-ish of whom are monozygotic. So on average, 100% genetically similar, roughly 80 dizygotic, so on average 50% genetically similar. This is a pretty old school EEG system. If you've seen EEG data before, you probably see 32, 64 channels, whatever. Here they only have 3, so very simple. And to me that was actually nice. So CZ is midline, right in the middle of the brain, and right in the center. O1, O2 occipital left and right. And so you can imagine then that I'll show some examples of this, but we'll essentially have a trivariate time series. Now, the way that they record it, or the way that they actually store the data, it is one long continuous recording. So Minnesota Twin Study is fairly rich. They did a lot of stuff, and so when they bring in the twins, so their rest state EEG is actually at the very end of the day, and where they ask them, hey, look, just we put the electrodes, scalp electrode on, and just sit here and think about nothing for the next 5 minutes. But when you've done a whole battery of, say, neuropsych exams and all these other things and surveys and all that, there were some people who, say, fell asleep. I mean, it's the end of the day, you've been doing a whole lot of stuff, and so there were some data quality issues. And they're a bit old school on also how they store the data. So even it is one continuous recording that's actually stored in what's called epochs. So you can think of it as just chunks of time series. And so when they do quality control, they do it. They just look at the epochs themselves. So this is I'm looking at 70 epochs, each one roughly 2 seconds. So that's about 2 minutes worth of data. And that's 70 times 128. That's how many time points you're getting of a time series here. Okay. I'll show you what some of that data looks like. But so let's go ahead and go to what are we going to do? So if I were to take one individual, that trivariate time series, and just plot it as one really long trivariate time series, this is what it would look like. So again, the data need not be contiguous in time. They were actually, usually they were, but not always. But this is what we're looking at. So this is just from one individual. Okay. Now what we want to do is, so this is all roughly 9,000 time points, roughly 2.5 minutes worth of data. What we want to do, so I'm going to zoom into just the first 2 seconds. Our goal here is to get something like this. So this is 2 individuals, top and bottom, their trivariate time series. Okay. And this is one individual and their corresponding co-twin. So what we want to do is to be able to take these time series data and then essentially start classifying them. You are in whatever state, you then switch to a different state, so on and so forth. So it's a type of hidden Markov model that we're going to be doing. Okay. But what we also want to do is make sure that that when we talk about, say, the blue state in the top individual, that's also the same as the blue state in the bottom individual, so that there's some alignment, that we can be talking about the same thing, that the colors make sense. That way when we start looking at, okay, at least for the person in the bottom, the blue seems to be the quote-unquote dominant state, what then can we, say about that particular state? And when we talk about that, that will also make sense for the top individual. Okay. So we want to do essentially one joint model for the twin pair, and so the model's on the pair level, not on the individual level. So to just recall what we're going to be doing here, or at least what our objective is. So the features of the data, right, is that we have it in epochs. There's 128 time points per epoch, corresponds to roughly 2 seconds worth. 70 epochs per individual, need not be contiguous in time. So we need to start, so we want to be able to model this in not just one long time series, but to, so we modeled epochs as well. And this is the challenging part, right? The twins themselves. Because monozygotic twins are, let's just say, we expect them to be quote-unquote more similar than dizygotic twins. We should then expect some similarities to come into play. More similarities for MZ twins compared to DZ twins. So the roadmap, so this is what the data will be. This the previous plot is kind of what we want to go to. That's actually the output of the analysis, and I will revisit that plot again. The roadmap for this is as follows. So what we're going to do here, this, by the way, so Michele Marina is going to sound familiar to you. I did not see your paper first. Is as follows. We're going to be defining this library of microstates, so that such as on the twin pair level. That way, when we start talking about features, it makes sense for both. This is where the beta process comes into play, and I'm not going to go into details about that. So when we go there, then once we have this library of features or states, we can then start, okay, here are the states that are available to me, let's now start modeling them using a HMM. So this is now a little, so these are states available, and so let's see what we can do. And once I have a state sequence, then I'm conditional on the state sequence and model as a vector autoregressive. So that's a fairly, that's at least the approach. And the key was actually the first one, namely that this library is defined for both. And that's where the grouping comes into play. So I think in the interest of time, I'm going to skip the overview of the Indian buffet process. I was going to show, here's an Indian buffet menu here in Irvine. So just to quickly run through it, is Michele choosing some dishes, then Martin Lindquist, doesn't like some of his dishes and chooses 2 more via essentially drawn from a Poisson. Then Martin tosses a coin on like, no, Michele, that's not good, and then he draws from another Poisson on how many new features, in this case, or new states that comes into play. Todd, there he is. I thought he was asleep. Is kind of digging some of it, and then I come in. I did not have hair when this picture was taken. But essentially, what's going on here is that it's on this feature selection, or we use the Indian buffet process to identify the quote-unquote states. So in the interest of time, I'm gonna be skipping some of this, and after that, it's just good old vector autoregressive model actually. So once we have the features, we can then we have the states that we know. We draw from the Dirichlet process, and then conditional on that, then we draw a state sequence, model it using a var. So what's behind the scenes here is that these 6 states have var parameters associated with them. And because we actually remove the mean from all the time series, anything that's driving the states is actually due to the quote-unquote connectivity, the intercorrelation between the trivariate time series. So this may look pretty nice, but recall that there's only 2 seconds worth of data. If we zoom out, it'll look like this. So these are the state sequences for both of them. They are not supposed to line up, by the way, because how you think the states that you are in need not be lined up temporally, synchronized with your co-twin. But what's going to happen here, though, is that when we start talking about the colors, the fact that the blue is most dominant for the bottom, that blue makes sense for, it's the same blue state for their co-twin. And from here, once we have those states, we can then start extracting features. And what we looked at was, okay, how long do these states last? And then we looked at just the correlation between the monozygotic and dizygotic twins. And indeed, we see that MZ twins tend to be more similar to each other in the microstate duration compared to DZ twins, suggesting the heritability component of microstates, which is confirmatory of, or is in line with that PNAS paper. But the number of microstates, it's not really heritable, but how long they last tends to be heritable. To just wrap up, this is not the end of the story. It never really is. And some of the questions that I've had for myself, on okay, what comes next, is why is there variation in those states? Is it because at the individual level, people do behave differently? Can we correspond and associate those states with some of the behavioral metrics that one could collect? Brian had to look at this while he was doing his work, and he wasn't really finding much, at least not in the analyses that we were looking at. But there's so some people in the dynamic connectivity world in FMRI have been correlating and have been finding things. And that's something that that we have unfortunately we haven't been as lucky on. Now this was on a trivariate time series. Of course, 32 to 64 channels is a little bit more common. Some it can go as high as 120 or 256. When you start considering more and more scalp electrodes, or if you're in the fMRI world, regions of interest, how then will this model perform? Can we relax certain assumptions of the model? And I've actually been inspired a little bit by Martin Lindquist's postdoc, Heather Chappelle, on this, namely, putting a model on the state durations themselves, leading to what's called a hidden semi-Markov model, and other things about that. about the model assumptions that we're making. What can we do to relax it so that it fits the data better. So I'll end here. So if you are interested further in this work, you can visit my website. The code is also available on GitHub. So if you want to have a look at that, so I'll end here. Thanks.
And because of the time, so we'll actually have a little discussion session after the speakers finish their presentation. So our second speaker is Ying from the Emory University. Yes, thank you. I appreciate that.
See, I didn't pay attention. Sorry, the things are there. There you go. And press the right ones.
Okay.
Yeah. And here's
Thank you.
Okay, thank you all for coming to the early morning session talk. So today I would like to thank Macaulay for organizing this year's SMI conference. And it's always great to come to this conference and see all those friends. And today I'm going to talk about a longitudinal ICA model for brain network analysis. So this is a joint work with my PhD student, Yikai Wang, and this is part of his dissertation work. And Yikai presented this work in a poster session on Sunday evening, so I apologize if some of you have already seen some of the work here. Okay, and so basically the goal here is for us to develop a longitudinal ICA for many of the longitudinal imaging studies now in the field. And this model was actually developed under a framework which we call the hierarchical ICA framework, which I'm going to briefly talk about today. So a brief background about ICA. So basically ICA is one of the computational technology in signal processing is used to separate observed multivariate signals. So a good example about it is a cocktail party problem. And then, so if you have several speakers in the room and they are kind of talking different things, they are called sources because they are generating kind of the signals. And then the data we observe are those collected by several of the microphones placed in the room. So this basically representing combinations of those source signals. And these are multivariate, observations. It's kind of generated as combination of those underlying sources. So using ICA under certain assumptions, if the data are really non-Gaussian distributed and also if the sources are independent sources, then you can use ICA to do a unique separation and recover those original soundtracks from those sources. So that is kind of one way to understand how ICA works. So in brain network analysis, ICA has been used mostly for decomposing the observed FMRI time series, which is like a 4D data, to recover the underlying component. Each of the components we say representing a specific brain network, and each of the network are composed of a set of spatially disjoint brain regions that kind of does similar things during the scanning session. So what you will see is that they have a similar temporal dynamics basically in their FMRI responses, so which we call the brain functional network. So the goal here is to decompose the observed FMRI data to recover the networks and then to characterize the spatial distribution, that is which region of the brain constitute each of the network, and also characterize the temporal dynamics, that is how each of the network functions across the time. So, and it can be written mathematically in this very nice, simple format. So this is basically like a 2D illustration of that decomposition. Typically what we do is that we kind of concatenate each of the 3D image into a row vector here in this Y matrix. So, and then you have the time representing the time series of the FMRI scan. So you have this T by V 2D dimensional data. And then what ICA does is to decompose this 2D data as a product of two matrices. So suppose if we extract the Q component from the data, then A will be T by Q, representing the temporal dynamics corresponding to each of the network. And then S will be Q by V, represent each row of the S will representing a specific, spatial map corresponding to a specific brain network. So this basically is kind of like the matrix re-representation of this decomposition we are doing here. And the key assumption in FMRI ICA is that the spatial source signals are independent across those ICs, basically. So, which is what you call the spatial ICA. And when people do ICA on EEG analysis, they sometimes do the temporal ICA and assuming independence on the temporal domain. Okay. So ICA has been used a lot to recover those functional network, as I mentioned. So actually, by this time, people have had a very good idea now in terms of what is the typical underlying brain networks. You can recover from fMRI data. So this is a very well-known paper by Stephen Smith in 2009, where they find consistent brain networks that you can recover using very large sample size from brain map, thousands of subjects, for example. And then you can find these brain networks both in task-related fMRI as well as in resting state fMRI. And so in our experiment, in our group's work across different data sets and different studies, we also see many of these networks coming up basically in our results from different studies. So I believe these results, those networks he recovered, is really pretty consistent across the samples and studies in fMRI. So basically, this is the classic model of the ICA. And then actually here, we extend a little bit and add the Gaussian residual. So that is called a probabilistic ICA, because the classic ICA doesn't even have this residual term. And the probabilistic ICA offers you some ability to account for the residual variabilities you don't get to observe in extracted ICs. So that is a very opinion property that our statisticians like. And also for our model kind of a build development, we found a probabilistic ICA offers more versatile, generalizations. And also it helps you to do the inference as well. So, but when we're looking at the classic ICA, it's very natural tool to apply for single subject fMRI data, because single subject fMRI data, you already have that multivariate observed signals. But then when we talk about multi-subject cases, and also the other different study designs where you acquire the images across in the subjects across multiple visits, such as pre-treatment and then post-treatment follow-ups, so that you have multiple fMRI collections in the same subjects, then this kind of data is kind of goes beyond what the classic ICA can handle, and you need some generalizations of your model in order to incorporate that. So basically, in the ICA field, to incorporate the multi-subject case, the method proposed by the imaging scientists and computer engineering in the world is called a temporal concatenation ICA. So, but for the longitudinal cases, we haven't seen available ICA methods, in the field to accommodate that. So this is a longitudinal fMRI study. So in the conference so far, we already hear several talks talking about, longitudinal studies. They have become really more and more popular now to study neurodevelopment and also to study disease-related as well as treatment-related changes in the brain. So, and then you can see in the field, like this kind of longitudinal studies have become more common than before. So this is a very powerful type of study design, because when study brain imaging, one of the very tricky thing is that there's a very high between subject variability and many sources of variations. So when we are doing cross-sectional study, for example, in psychiatry study, to looking at what brain part is causing certain psychiatric symptoms, that kind of association in cross-sectional study is often confounded by many confounding issues that is very hard to tease out in cross-sectional study. Longitudinal study, because you're observing the subjects repeatedly across time, so you can looking at the interplay between that subject's brain changes and also the clinical symptom changes across time. So you can study that association within the same subject, using he and her as her own control. So that idea, basically, that will provide much more promising, tool for you to identify some reliable association. And also, like another main advantage of the longitudinal is that it can potentially offer the possibility for us to tease out the association versus the causal, because it is very hard to tease out the causal effect in the brain studies. In longitudinal study, actually, is something that can help to find some solution, because if you see some changes in the brain that predict, the changes in the clinical symptom, but not vice versa, that kind of is one way to help tease out the causal effects, actually. Okay, so these are the advantage of longitudinal study. And in terms of the data example, so ADNI data basically, has been criticized a lot. But when the time we started this work, when you're looking at longitudinal imaging data with a reasonable sample size, there wasn't many options back then. There are more now, but back then it wasn't that many. So basically, the ADNI2 is actually was one of the field studies that does offer public available, longitudinal data. So they have collected data from ADNI subjects and also two MCI groups, early MCI and late MCI, as well as normal controls, and then image them repeatedly across time, every 6 months. And then basically we use the data that's from baseline year 1 and year 2, and we got kind of cut there because if we extend it even longer, then your sample size goes down to low at that point. So the scientific question is, what is the difference between normal subjects and ADNI subject at a given time point? And then when we're looking at ADNI subjects, what is the changes in the brain across the visits? And also, like another question is, what is the difference between early MCI and late MCI, basically? So what can we do using existing ICA methods to handle longitudinal data? First option, you do separate ICA within each of the subjects, separately across time, and then you try to put them back together for the longitudinal analysis. But that's very challenging because ICA has some challenging issues called, for example, is like order invariant. So it's very hard to kind of compare ICs or match ICs from separate ICA runs. And also, like ICA is stochastic, so if you do ICA separately at different time points, those ICs comparability is questionable. And another way is to do TCG-ICA type of analysis. What you do is that you concatenate all the subjects' data across time, across subjects into this very long vector, and then just decompose it in a two-dimensional classic ICA decomposition. And then you try to using like a dual regression as secondary analysis to recover the subject-specific spatial IC maps to do the longitudinal ICA. But we have, based on our experience with dual regression, this type of two-stage separate analysis tends to give you very noisy estimates, and you lose efficiency basically in your estimation. Okay, so what we do is called what we resort to is a framework, what we call the hierarchical ICA framework. So basically, this is a framework that we found to be a very general and versatile framework for modeling various sources of variations in brain networks, such as between subject variabilities and subpopulation effects. The idea here is very simple. For statisticians, this is kind of like no-brainer. It's multi-level model. On the first level, you do the subject-specific IC decomposition, and then on the second level, you took the subject-specific IC maps and model out those specific, various sources of systematic variations you try to capture, population effects or subjects' covariate effects and time effects in a longitudinal ICA, for example. So, and here is kind of like a little bit history about methods developed under the framework. The first hierarchical ICA work appeared in 2013, where we just put subject random effects on the second level model. So it's very simple and just accommodate between subject variability in that. And then for estimation, we derive the exact EM, which offers exact solution in E step and M step, but it's very slow. So I worked on this, what we call a variational EM. Basically, this is from the variational base type of work. You get a variational factorial in a posterior distribution. So you can get around that very time-consuming part for fast computation. And then later, a major step forward is called this hierarchical covariate adjusted ICA with my PhD student, Ryan Xu. And then this one, it allows us to capture covariance information in the second level model. So you can modeling out those between group differences and continuous covariance effects. And so the estimation-wise, a major step forward is that we propose this subspace-based approximate EM. Because variational EM has its own issues. It involves kind of, you have to do additional optimization for that variational approximation distribution, and sometimes they give you convergence issues. And also, when you change the model, you have to rederive your variational solution. So the reason, the subspace EM I'm going to talk about in a minute is based on observation, is that you don't have to kind of consider the whole space of the latent state variables, but rather you can find the posterior mass is concentrated on a very small subspace. So you can do your EM based on that very small subspace efficiently, and that will give you a very good, a lot of improvement in the computation. And then the longitudinal ICA, which just appeared this year, is another step forward so that we can incorporate longitudinal effects and within subjects repeated scans. And in addition to the previous EM algorithms, EK also has an idea about voxel-specific subspace EM that he thinks will be a major step to increase the speeding. And finally, recently we have worked with Amanda and in the template ICA, and basically the template ICA is that if you have some large populational study like HCP, then you can derive some empirical population priors on your brain networks, and you can feed that into your second level model, and then on top of that, you can add some subject nuisance ICs to representing that subject additional variability. Okay, and then for estimation, Amanda has derived a new fast two-stage EM algorithm. That is, if you do have this empirical population prior available to you, you can further speed up your computation, basically. Okay, so this is the longitudinal EM and longitudinal ICA model. So just a brief introduction about notation. I here represent the subjects, and J here represent the time, and XI represent the time covariance of the covariance from the subjects. Okay, and then this is the LICA model. Again, we write it out. It's very simple model set up. First level is a single subject's decomposition. On the second level, basically you take the subject-specific map and then kind of model it, parsing it out into various sources of variability. So basically, like this is kind of like the population brain maps. So this is kind of like functional network in Stephen Smith's paper that you can consistently identify across subjects in the population. And then this is the time effects that is common across all subjects. For example, when you collect the scans across time, different time points, sometimes if you have some systematic variation in your collection, like time scatter effect, for example, then this kind of is trying to capture that population time effect. And then we have this covariate modulated subject time effect. So if you have a different, for example, disease groups, like Alzheimer's disease groups, then they may have a different changing pattern across time that is captured using this covariate modulated time effects. And then we have the BI, which is the within subject random effects capturing the within subject variations. That is the unique brain network patterns observed with the specific subjects. And finally, you have the additional variabilities. So that's all. That's what the model is set up. Okay, so this is kind of like a schematic plot for the model, and then for each subject you have FMRI data collected across K visits, and then you have multiple subjects. So you do the single subject decomposition on the first level. Oh, by the way, one thing I want to say is that even though the model is two-stage, when we estimate it, it's holistic estimation. So all the parameters are estimated jointly at the same time. So it's not a two-stage estimation, basically. And this one-step holistic estimation is important because that's what you gain extra efficiency. Okay, so basically this is the first stage model. Once you kind of get the subject-specific decomposition, then basically you take those subject and time-specific map of the brain network to the second model, to the second level model, and then you model it in terms of the population, that is what's common across subjects. And then in each K visit, you add that common time effects that is the same across all subjects. For example, if the study changed Skinner, from visit 1 to visit 2, and then everybody's brain network will be changed, because of that effects. That's going to be captured by this population level time effects. Then, based on the subject's covariate, disease group and treatment group, then they can have this modulated time effects. And finally, we add back the subject-specific unique brain network characteristics back to that subject's, repeated scans. So that is kind of like, and then for the model, we kind of using our mixture of Gaussian source distribution to model the underlying population ICs. So the idea here is basically the mixture of Gaussian has been shown to be a good biological, meaningful source distribution to capture that mixture pattern in the brain network. So what happens in the brain network signal in FMI is that in each of the network, the signal across most of the voxels in the brain are kind of random variations. And then, but then you have that collection of voxels that belong to that network that has activation or deactivation signals. So that is well captured using kind of mixture of Gaussian type of, distributions. And we also designed this state latent variable for each IC and each voxel to show, which, it's black. 5 minutes or 2 minutes? Okay. Okay, so that is one. So I think I'm skip forward, and then you just have to trust us that we solve this estimation issue. And so we derive the E step and N step. And then, so it looks ugly, but actually it is a nice algebra exercise. So, but we did have you can get explicit E solution and solution. And then for our estimation, we have this basically a subspace EM. So you kind of, you can basically find most of your posterior masses in this kind of a subspace. So instead of doing that whole, whole space, you can just reduce to this subspace. And this is the one that EECA is trying to work out, voxel specific. And we also work out the inference, and it's approximate inference, because of variations to do that. Okay, once we have that, then you can test the hypothesis testing. Basically, you can test at each time point what is the group difference, and then what is the longitudinal difference within the within one group, like admin group. How does them change from time to time? And then that can be basically constructed using this type of linear constraint-based test statistics. So I skip the simulation. Just one thing to show. This is basically what happens with LIC truth, LICA, and TCGICA. One of the things with TCGICA is that you're kind of having this convergent effects. So if you're looking at the changes across time, TCGICA tends to kind of regress everything towards the mean. So basically, you kind of got less power to detect the changes from baseline to the later visit as comparing to the LICIA. Okay, so the thing I really want to talk about is I'll also skip the data application. And one of the things we observe is that in-admin data is very noisy. So we didn't find a very consistent, increasing trend or decreasing trend in that time period. But again, it's only 2 years. Maybe the time window is too small for you to see some dramatic change. But we did find more variation within the admin data, admin subjects. And also we found the EMCI, early MCI people, when you're looking at the brain maps, they are more closely resembled the control subject, while the late MIC people will more closely resemble the admin subjects. So there are something kind of making sense, in this finding. So I don't think we need to trash everything in admin study, basically. It's just one thing I want to say. Yeah. Okay. And then the thing I really want to highlight is that we developed the MATLAB toolbox for the hierarchical ICA work. So we are trying to incorporate LICA into this framework. Currently, it implements the hierarchical covariant ICA, basically. And then you can see that from, download that from every GitHub. And we also has a video tutorial for this, which will make it easier. So it has the data input. It can input both NIFTY files and also as well as MATLAB files. And then this is basically, you can specify in the model, you can incorporate what covariates you want to add into the model. You can also add interactions of your model and choose what is your reference group when you do between group comparisons. This is an analysis model. It runs that efficient subspace EM on the background, but it offers you also this real-time status monitoring window, so you can see how your EM algorithm is improving across the iterations. You can also stop it manually if you think it has already stabilized in the EM algorithm. Okay, and then this is kind of like analysis. We have several visualization output. All of them are kind of like, interactive. So you can click point on the brain to show you what is the longitudinal trajectory of a specific brain locations across the longitudinal studies. You can also record what are the voxels that you have clicked and to save that profile plot. And you can also do between subpopulations, like disease group, any group versus control group, just by putting in what kind of a covariance group you want to compare for. You can also, we also has this user-specified hypothesis testing window where you can specify the specific linear contrast, and then the program will do the hypothesis testing and output what is a significant effect for that. Okay, so that is, you can also see the subject-specific brain network to help you identify any weird subjects or unique subjects from your study. Okay, so and we do want to validate our findings by further, when we get more data from ACME2, when we have more data sample size, then we want to go back there and see whether we can replicate. And so acknowledgement, Ikai, he's basically the main driving force behind LICA. Josh, and is another PhD student in CB's group that did most of the backbone job for the behind hint, MATLAB toolbox. And that's Amit, which is a senior software engineer. And finally, just give me 5 seconds. Oh yeah, just want to say, like in next year, so we have been lucky to give the opportunity to host the SMIs in Atlanta. Since we cannot compete with Irvine for this gorgeous weather, so we have to start our advertisement as soon as possible. So it's gonna be similar time in Atlanta, and I hope it will be another great event like this year. Thank you all.
While Amanda is preparing for next presentation, we can take a quick question. Anyone has a question to either Mark or Ying? Yeah.
I have a question for Mark. It was very interesting talk, Mark. Especially, I'm just curious about the similarity you were mentioning between twins, right? And you're saying maybe there's something in the resting state and connectivity, underlying states between twins and stuff. We've been observing, I was just curious if you guys observed also any similarity in spectral density.
Yes.
For twins, because we have a study on EEG where we scan a person's day 1 and we scan them in day 2. And if you scramble the spectral density of people coming from different days, you can't match them from day 1 to day 2.
Right.
It's kind of like a jigsaw puzzle, you know what I mean?
So if I paraphrase your question, is the spectral density of EEG time courses, are they heritable? Short answer is yes. So that was actually Brian's previous work. We also did a Bayesian non-parametric approach, but that's I can point to the literature. People have actually been looking at that since the 80s and 90s. And not only is the spectral density itself heritable, but specifically different frequency bands within are heritable. Namely, and even the location of the peak, usually for resting state EEG is alpha peak, that's heritable too. So short answer is yes.
We have similar things. I mean, even day 1, day 2 is similar.
Yeah.
So it's kind of like a signature, maybe.
Yeah. So there are. So you're talking actually about within subject now. So yes, I'm not surprised to hear this, and we should chat a little bit more too.
We have some technical difficulties, so we have some time to ask another question for Ying. Yeah.
I had a question for Ying. I was just wondering, it reminded me, you're doing it with ICA, but it looks almost like, for functional data, like an analytical system, right? In functional data, you have it like a variation for subject, variation for visit.
Model-wise, it does represent a constitutionality, but then distribution-wise, then that's a difference. Do you use your HTML also? But in ICA, the key assumption is that the signal has to be non-positive.
Oh no, because I had to be Mac. So
Yeah, but that's right. Just the model. Yeah, that's why I'm saying it's a very simple model.
That's very great.
Oh, there goes. Perfect.
Yes. So finally it worked.
So now we're going to introduce the question: how many statisticians do you need to present?
Yes, our
a
last
slide?
so our last speaker of this session is Amanda Meja from Indiana University. Welcome.
Thank you. Thank you so much to McKelly and all the local organizers for this amazing event. I've been super impressed at everything that you guys have been able to put together here. So should I use the microphone? Is that helpful? Okay, I see nods. Okay, so I'm going to be talking about a project that I've been working on for a couple years now, really, with some amazing collaborators, developing a meaning computationally tractable spatial Bayesian modeling approach for task fMRI that's been projected to the cortical surface. And I'm actually going to focus a lot of this talk on a current analysis that we're doing with my collaborator Robert Welsh at University of Utah of his study of subjects with ALS, which is a motor neuron disease, more colloquially known as Lou Gehrig's disease. And part shameless plug, but part explanation for why I'm not going to go into great detail on the methods is that our paper just came out pretty recently, and so you can see all the technical details there. And it's somewhat involved and could take a long time to go through in detail, so I'm not going to spend very much time discussing the methods, just kind of give the broad strokes. Okay, so an overview of the talk today is, first of all, why should we use cortical surface fMRI data as opposed to your traditional volumetric fMRI data? And then why should we take a spatial modeling approach to task fMRI? Second, I'll talk about the basic, give a basic overview of our statistical modeling framework. Again, not going into too much detail there. And then also give a very brief overview of our validation studies that also appear in the paper that show how the method performs in simulated and real data from the Human Connectome project. And then I'll present the ALS study that we're currently working on, and the results I'll be showing are very preliminary. So my collaborator has been kind of leading the charge on getting the data processed into the right format, which takes a lot longer than you might think if you've ever tried to undertake cortical surface processing. So after many months of working on that, we have data. It's been quality checked a million times, and our models are running, and now we have some results. So this is really very preliminary, but I'm excited to share what we're seeing in this ALS study, and how these methods are advancing studies like this by enabling us to do accurate subject level modeling. Okay, and then also just talk about some current and future directions of the work. Okay, so first, why should we use cortical surface fMRI data? So maybe number one answer is that it's now available through the Human Connectome project, and it's beautiful, and you don't have to spend a year necessarily processing your data into that format if you're willing to use the Human Connectome project. And that's really how I got involved in cortical surface analysis, is through that data set. But why from a more conceptual standpoint? It's really about the spatial dependencies. And so if we want to leverage spatial dependencies in fMRI data, using volumetric data is really not ideal. So there's a couple issues with volumetric spatial dependencies and also just volumetric data in general that I'm trying to illustrate here. So first of all, what are we looking at? So the blue and the red are two different subjects, and this is their cortical surface gray matter segmentations. And so you can see that basically they kind of overlap in a sense that they take up the same chunks of the brain, right? So you can see in this image maybe it looks like they overlap pretty well, but when you zoom in you see that the folds are completely different. So they may represent the same basic functional areas of the cortex, but the actual directions and the orientations of the folding patterns are completely different between these two subjects. And this is after our best efforts at realignment. So these subjects are registered and normalized into the same template space. So this is basically the best that we can do in volumetric space. We can't really go in there and start moving around the cortical surface without really messing up things in the volume. And so the alternative is to look at the cortical surface itself as kind of a manifold. And one of the nice things about that is we can better align subjects, right? So if we do a group analysis, we actually have more comparability of the locations of activation across subjects. So we should get more precise estimates of activation in different locations. But also, we can now leverage spatial dependencies in a way that makes a lot more sense. So in volumetric data, if we're talking about spatial dependencies being a function of distance, then you can see that there's a lot going on, right? So we don't just have cortical gray matter, we have white matter, we have cerebrospinal fluid. So locations that are nearby in space may be actually from completely different tissue classes, and they will not have similar activation patterns, whereas our model does assume that they will have similar activation patterns. Another issue is the folding. And so, for example, in this spot right here, you can see that there's two parts of the cortex that are right next to each other, right, because of the folding. And so if we're depending on Euclidean distances in the volume to tell us anything about neuronal dissimilarity, it's not going to do a great job. If we transform the data into the cortical surface format, we can actually use the distances along the cortex. So these are now geodesic distances. And those distances are going to tell us a lot more about neuronal dissimilarity. Okay, the whole idea, though, about using these distances is that if we can take a Bayesian approach or even a non-Bayesian approach to leverage the strength across locations, we can improve our estimation and we can improve our inference, and maybe we can avoid depending so much on leveraging information across subjects. So we certainly do want to leverage information across subjects when we are able to do so, and perhaps when it's useful for some kind of group analysis. But in many cases, we actually are interested in subject-level activation patterns and subject-level cortical organization. And a lot of our current modeling approaches don't really allow us to do that kind of analysis in a very accurate way. So we hope that by borrowing strength across locations, we will be able to obtain better estimates of single subject activation and cortical organization. Okay, so just to give I don't really want to go into detail here, just to give you kind of a brief understanding, a very baseline understanding of how cortical surface data works. And so the volume is used to establish the white matter and peel surfaces, so that's the boundaries of the cortical gray matter, which are then projected to different inflation levels. And so the data itself, so for example, the functional MRI data is projected to the cortical surface in terms of getting some numerical values of activation or of bold signal. And then those values are kind of fixed. But the actual locations of the cortical surface can change depending on the inflation pattern. So you basically have a matrix of data values and then some kind of mapping to the locations on the cortical surface. This is actually one of the most confusing things for me when I was starting to get involved in cortical surface analysis, is that I didn't understand the division and the separation between the data and the locations of the data in the brain, right? So in volumetric data, you always have your data representing both locations and the data itself, right, the values. So they're kind of actually separated in cortical surface analysis. So you can you can kind of inflate to a white matter surface, or that's the original surface. You can inflate to an inflated surface, a spherical surface, and then at the spherical surface, that's when all the intersubject registration happens. So they use this inflation to the spherical surface to align cortical folding patterns across subjects. But then those, so basically the data is linked to those locations, which are now linked across subjects. But the surfaces themselves can then be back deflated into a subject level surface, or these different template surfaces, like the mean white matter, the mean inflated surface across subjects, the mean white matter surface across subjects. So we can use these different surfaces to both do visualization, but also to do analysis that depends on the spatial orientation of the data. Okay, so that's kind of cortical surface in a nutshell. All right, so I'm going to be very brief here. The classical GLM would be a massive univariate approach that will have a lot of downfalls, such as spatially smoothing, failure to account for spatial dependencies, and some issues with multiple comparisons. So these have been rehashed many, many times in the literature, so I won't go into detail. There's also some problems with the traditional Bayesian alternative. So there have been spatial Bayesian models developed for volumetric FMRI, but these do run into some issues. So it's difficult to find an appropriate spatial prior. The alternatives for computation basically been variational Bayes for a long time. There's some work now at MCMC, but variational Bayes has been really the main tool, but it has a lot of problems with accuracy and specifically with underestimating the posterior variance. For inference, marginal posteriors have been used, but this leads to multiple comparisons, and then group level inference has not been undertaken in the literature so far. It's all been subject level. Okay, so to give a very brief overview of our methods, so I'll talk about our single subject modeling approach. We are now extending to group, or we do extend to group level modeling, since that's also an important type of analysis that people want to do with fMRI data. And then I'll give our simulation study in a nutshell, our human connectome project data analysis in a nutshell, and then talk about computation times. Okay, so the first step is to construct some kind of triangular mesh. So this is actually the format of the data. So it's no longer kind of a lattice like you think about in volumetric fMRI. And so that is actually the format of cortical surface files, GIPD files, .gii. So that's kind of convenient. But one of the nice things is that you can actually interpolate to lower resolutions without losing any kind of properties of the prior. So I'll talk about the priors in a second. But you can use these connective workbench tools to go from, say, a 32,000 resolution to, say, a 6,000 resolution, which is what I'm showing here. You can also construct a triangular mesh volumetric fMRI data. So there I'm showing a slice of data where we've constructed a triangular mesh to represent the data locations, and the data is then interpolated into those vertices. One of the nice things is that you can also mask the mesh to focus on certain regions to reduce the computational burden. And then also the mesh provides smoothing around the borders, so we no longer get this kind of blurring of boundaries between, say, brain and background. All right, so step one is to assume, so this is our model. I'm not going to go into detail about the model, but basically the beta k's represent our task activation fields. And we're assuming a spatial prior on each of these activation fields, so we assume that they're basically smooth. And the type of prior we're assuming are stochastic partial differential equation priors. These are really the only class of priors right now that are available for triangular meshes, but they're actually also a really nice type of spatial prior. So they approximate a continuous Gaussian random field that has Maturin covariance with a Gaussian Markov random field that gives us a sparse precision, and that leads to computational feasibility. And so as an approximation to a continuous field, they're actually invariant to finite resamplings of that continuous field. So it doesn't matter from a theoretical standpoint whether we have 32,000 locations or 6,000 locations, the underlying properties of the spatial field are actually the same. Again, it's constructed on a triangular mesh, the format of the cortical surface fMRI data, and then is able to apply appropriate smoothing along boundaries. All right, so step two is to do the actual posterior computation. And so we use INLA to estimate the posterior quantities, like the posterior mode or the latent fields. And INLA is an entire area of research into itself, so I won't really talk about INLA today. But it's fast and accurate, so that's why we use it. And it also works well with these SPDE priors. So step three is to identify activated regions. So this is a big step in task fMRI, is to identify regions of activation. Typically this is done using hypothesis testing and a frequentist framework. And in previous Bayesian methods for volumetric fMRI, this was typically done using the marginal posteriors. So here we are using actually the joint posteriors using an excursion set method to actually identify jointly areas that are activated with a certain probability, with a certain joint posterior probability, and at a certain activation threshold. So we can say we're interested in locations that are showing at least 1% signal change due to this task. So we don't have to threshold at 0, so we can actually take into account the effect size, which is also an area of interest right now in functional MRI. Okay, so for group level modeling, again, this is a gap in the literature for 5 minutes. Okay, so this is a current gap in the literature. So I'm gonna go ahead and skip ahead. So basically, we propose a joint modeling approach that takes the subject level posteriors, combines them to get posterior inference at the group level without having to fit all the subjects together. And it's scalable and fast. And so that provides a nice alternative for group inference. All right, so I'm going to skip the details of the simulation study, and I do want to just mention briefly how fast is fast. So after some kind of, the biggest thing is to take some steps to reduce the complexity. So we do some resampling, we separate the hemispheres since they're actually separate meshes. But a big step for us was doing things like nuisance regression, eliminating the baseline field, pre-whitening the data, try to reduce the number of hyperparameters as low as possible that still kind of captures the essence of your model, because that's a big issue for computational burden. We also use INLA Partiso library for parallel matrix linear algebra, and that has huge computational benefits. And then using our joint approach for group analysis, we can also parallelize within that. Our subject level model estimation, we ended up getting that down to 30 to 45 minutes per subject with 40 to 50 gigs of RAM. When we first started, we were looking more like 5 hours with 200 gigs of RAM. So these steps that we took had a big impact on computational burden. The joint group level approach, including identifying areas of activation, only takes about 25 to 30 minutes. So we were happy with these, especially compared with our previous efforts that were taking a whole lot more resources. Okay, so now I want to talk a little bit about our study that we're doing currently. So this is a study of ALS. Stephen Hawking is probably the most famous person besides Lou Gehrig who has had ALS and been in the public eye. So this is a very diverse disease, so we really want to be able to study things at the subject level. So Stephen Hawking is actually a great example of the diversity of this disease because he survived over 70 years. Median survival, or he lived to be over 70 years old. Median survival is actually 2 to 4 years. So he way outlived the expected duration of this disease, but it just is an example of the great diversity of this disease. And so if we study things at the group level, it's really not going to tell us a whole lot about disease progression and treatment and things like that. So we want to be able to do subject level analysis, but our data is extremely noisy, so it's a big challenge. Okay, so just to skip ahead to some of our results, I'll put this on my website. Okay, so this is a healthy control subject. We have longitudinal data. So this is a motor task, and I'm going to show the different visits. So you can basically see the same area of the cortex. This is a finger tapping task. It's basically activating at every visit. There's a little variation. But then we looked at basically all of our subjects and kind of the size of the areas of activation over time. And what you can see is with the healthy controls, like what I just showed you, is it's pretty stable. So within the left hemisphere, we're expecting to see activation. Within the right hemisphere, we really don't expect to see any activation for this task. With the ALS subjects, we see a lot of things happening. We see overcompensation, and then we also start to see some complete loss of motor function. So you see this kind of inverted U shape for some of the ALS subjects. We're also seeing in the right hemisphere what's called lack of inhibition. So basically that the brain is not able to stop the left hand from doing what the right hand is doing. So you may have seen this in motor neuron diseases if you've had any exposure, is that when I tell my right fingers to tap, my left fingers can avoid tapping. But in motor neuron diseases, you'll see subjects basically doing this. They're not able to inhibit the signal passing from the left side of the brain to the right side of the brain. So we see some of that happening here as well. And so just to show you some of these individual subjects, for this subject, A26, we see this growth of the activation areas basically representing compensatory neuron firing. And then eventually we see that start to die out. So we just start to see the activation overall just plummet in these subjects' brains. This is another very interesting subject. This subject was the subject who was in the study for the longest time, 4 years, and had a very slow progression. And with their data, we see this compensatory behavior in the left hemisphere of the brain, but then we see it start to fade over time. It's a very much more gradual process than we saw in the first subject. So I'll wrap up there. We want to continue to explore and quantify these differences in healthy control and ALS subjects in the study. Very excited to be able to look at this data at a subject level and to hopefully provide some insights into this disease that is very difficult to study. So we've talked a lot about Alzheimer's today. ALS is a much more rare disease, very debilitating and very difficult to study, in part due to the very short survival of these subjects. So having access to a data set like this, where we have several years of data for a number of ALS subjects, is a pretty exciting opportunity. We're working on some method extensions. I won't talk about those right now. Currently working on software, so I'm very excited to get that available to people to use with a great team here at the R workshop we had a couple days ago. And also just to say thank you to everybody, and also shameless plug. Currently recruiting a postdoc, and I just want to illustrate here how beautiful Indiana University campus is in all times of the year, so in all seasons. So no big deal, just, like number 15, most beautiful campuses in the country. We really enjoy it. So thank you very much to everybody. Thank you for the organizers and to the moderator and to my collaborators.
So now it's time to take a question. So is there any question?
Yeah, very specific perhaps. Why Matern? So I know that Matern covariance is used in spatial statistics because there are lots of discontinuities and other things. So is that also relevant here for modeling the spatial activation?
It's thought to be, so I think that the selling point of, one of the selling points of the SPD priors is that because it approximates Matern, it's a lot more flexible than a lot of the Gaussian markov random field priors that have been previously used. So you have a couple of parameters that control the Matern spatial dependent structure, and that they're a lot more flexible than the other Gaussian markov random field priors that are being used. But I mean, that right now it's really, to my knowledge, the only alternative to kind of more traditional lattice-based Gaussian markov random field prior. So it represents a big advance from my understanding. But spatial statistics is not really my area of expertise, so I will defer to my collaborators on that question. Happy to talk about it further, though.
Yeah.
Why is it better to do the registration on the sphere rather than start
Yeah.
and then?
Another area that's not my area of expertise, but so the papers that go into that are these Fischl papers from 1999. They talk about all the the surface inflation. It's like all these optimization problems, and so I think, if I have to guess, is that it's probably maybe the only option that's computationally tractable besides doing it on a flattened surface. So I'm not actually super familiar with the details of how they do that registration, but I think that they would find it very, very difficult to do it on the individual surfaces. So first of all, at least on a sphere, you have the same size and the same orientation of all the locations. So I think it's probably just a lot easier. The problem with the sphere is that it distorts the distances, but it maintains basically the relationships between the vertices. So you can keep the same mesh, basically, structure, but the locations change. So if you're using it for spatial analysis, then the distance distortions can be a problem. But I think that because you can basically deflate back to other levels, then it is not too much of a problem if you're, kind of going back to a regular surface. So sorry, I don't have a great answer for your question.
So, any questions? Yeah. Then let's finish our session.